So now we can transform our non-dimensional equations back to the dimensional ones. The continuity equation is very very simple to do, right? du not dx naught plus du not dy naught equals to 0 when gotten back to the dimensional form. We just get back the continuity equation, which is du dx plus dv dy equals to 0. This is simple. And here, the ns equation in the x direction, if we transform it back, say u naught is equal to u over u, right? So we plug all those dimensional variables into the equation, and the final form we get should be du dt plus u du dx plus v du dy equals to minus 1 over rho dp dx plus nu d squared u dy squared. Do you agree? This equation we get is much simpler than the original form of the ns equation. Okay, basically this is our result. The two equations combined, we can call it to be the Prandtl boundary layer differential equations. Okay, differential equations together with the boundary conditions. What will be the boundary conditions? When y equals to 0, when y equals to 0, our velocity will be 0. Also, u will be 0. And at y equals to infinity, our velocity won't be affected by the boundary, so it will be the same as the mainstream velocity, right? But it seems we lost some information, did we? We started with 3 equations, but now we only have 2. Is it indeed the case? Well, did our analysis on the ns equation on the y direction is a total waste? Is it a total waste? It is not. Remember, we got a conclusion which is dp dy equals to a very small number, right? So if this is a very small number, then transformed back to the dimensional form, we can say dp dy is equal to 0. What does this tell us? That the pressure doesn't change in the boundary layer in the y direction, right? So if we take a cross section, the pressure here, we can say it's a constant. So the pressure at every point in the cross section in the boundary layer will be the same as the pressure here. That is the pressure outside of the boundary layer. I didn't tell you before, but maybe let's do it now. We said the Reynolds number is very high in our problem, right? So if the Reynolds number is very high, it means Reynolds number is what? U times L over nu, right? It's the ratio between the inertial forces and the viscous forces. So if Reynolds number is very high, then the effect of viscosity is very low. If the viscosity is very low, we can treat the fluid as ideal fluid, and then we can use the theory of potential flow, right? So in a sense, we can treat the fluids outside of the boundary layer, which are the fluids that are free from the effect, free from the influence of the boundary, to follow the potential flow theory. So the pressure there would be very easy to calculate, right? And outside the, so we can, in solving a problem regarding the boundary layer, we can say the pressure is known because the pressure outside is known. So the pressure at the boundary of the boundary layer will be known. And dp dy is a constant, so the pressure inside the boundary layer will be known. So actually, here we have 2 equations, and we only have 2 unknowns, u and v, right? So theoretically speaking, this is a closed system. We can solve it.